Geometry begins with a clean distinction between two concepts. Perimeter measures the one-dimensional boundary length, while area quantifies the two-dimensional surface covered. This distinction dictates how we scale units. Because area exists in two dimensions, converting 1 square meter to square centimeters requires squaring the linear factor. The result is 10,000 square centimeters, a far more significant shift than the linear change from 100 to 1. Early Indian temple architecture shows this logic in practice. The Shilpis, or traditional architects, applied different sets of measurements for the massive boundary walls of this complex than they did for the vast paving required for the inner courtyards. Confusing these two values on a test breaks the physical logic of how we quantify space. This physical logic also defines pi. Pi is the fixed ratio of any circle's circumference to its diameter. No matter the scale, c divided by d remains constant. Common shortcuts like 22/7 or 3.14 are merely approximations. Pi is an irrational number. Its decimal expansion extends infinitely without ever repeating or ending. By alternating a series of odd fractions, Madhava of Sangamagrama defined pi exactly around the year 1400. His discovery predates similar European infinite series by roughly 2 centuries. Recognizing pi as a structural ratio born from the circle allows for the reliable measurement of any curved environment. Measuring parts of a circle requires selecting the correct dimension. Both arc length and sector area use the same central angle fraction, theta over 360, but they scale different base formulas. Arc length uses the linear circumference, while sector area uses the total squared area. This choice defines the construction of a standard 400-meter athletics track. The offset start lines seen here compensate for the larger radii of the outer lanes. Without a stagger, runners on the outside would travel a significantly longer arc than those on the inside. The exact distance of this head start is found by multiplying 2 pi by the difference in the lane radii. Ancient Indian epics describe similar chariot race arenas that employed these offsets to ensure competitive fairness across curved tracks. In straight-edge geometry, area depends on a principle called shear invariance. As long as the base and perpendicular height remain constant, a parallelogram can be pushed sideways without changing its area. This height must be measured as a perpendicular line. Using the slant side instead of the true height is a frequent point of failure. If height and base define polygons, we can prove the area of a circle by transforming it into one. By slicing a circle into thin sectors and interlocking them, we create a rectangle. The width equals half the circumference, pi times r, and height equals the radius. Nilakanta Somayaji used this method around 1500 CE to prove the total area is pi r squared. Understanding these transformations removes the need for blind memorization. Land surveying often requires measuring triangles, where a perpendicular height is impossible to determine physically. Heron's formula calculates area using only the 3 side lengths. By finding the semi-perimeter and checking it against the triangle inequality, we can find the exact area of any valid triangle. In 628 CE, the mathematician Brahmagupta generalized this logic. He developed a formula for cyclic quadrilaterals, 4-sided shapes whose vertices all sit on the boundary of a single circle. This is Brahmagupta's equation. Unlike Heron's formula, there is no semi-perimeter S factor multiplied outside the root. We can see the relationship between these formulas by shrinking one side of this quadrilateral, side D, down to 0. As the shape collapses into a triangle, side D disappears from the math. The final term becomes S, and Brahmagupta's formula reduces precisely into Heron's formula. Geometric mastery comes from recognizing how every dimension, shape, and formula connects within a unified architecture. Visit edunudge.in to practice with CBSE-aligned question banks. Our 5-step nudge system helps you navigate the geometry of space without simply giving away the answer.